Hi everyone, welcome to Reason with Science. I'm your host Jitendra. This is a conversation with Ramanarayanan Krishnamurthy. Ram is an associate professor at the Scripps Research Institute in the chemistry department. His research group works on prebiotic chemistry with a focus on origins of life. In this conversation, we talk about major hypotheses proposed for origins of life. What is life? Hype created by media, what origins of life research is lacking, and Ram's views on faith and science. I hope you enjoy the conversation. Share and subscribe to support the podcast. Thank you for listening. Hi Ram, welcome to the podcast.
Yeah, thank you. And it's a pleasure to be on this. And again, thanks for this invitation.
Yeah, so tell us a little bit about your journey to reach at the Scripps Institute.
Okay. I was born and brought up in Chennai, India. Um, from a young age, I think I had a great interest in chemistry, especially synthetic organic chemistry. And that led me to do my bachelor's in Vivekananda College under the auspices of University of Madras. And then I went to the Indian Institute of Technology, Bombay, IIT Bombay, to do my master's. And from there, I left to the US to do my PhD. Got my PhD working with David Hart at Ohio State University. And it is during that time I got hooked into the origins of life. In 1991, there was a very beautiful lecture by Albert Eschenmoser, who is one of the leading synthetic organic chemists at the time. And he gave a lecture which was titled, in German, it was called Warum nicht Hexose Nukleinsäure? And in English, it would be Why not hexose nucleic acids? And I thought that was a very strange title. Who would, ask such a question? Because, everybody knows it's RNA and ribonucleic acids. And once I sat through the lecture and I listened to it, I could not have think of anything else. I just simply fell in love with the way he was approaching and using the tools of synthetic organic chemistry to answer fundamentally important question: why nature chose the molecules it did for its life. So, and then that led me to write to him. In those days there were no emails; it was all snail mail, if believe it or not. And I had to write a letter to him saying that how I really like his lecture and I would really like to work with him. And it was 6 months before I heard in the positive. He said, yes, you can come. And then I was so excited. I went to my professor, David Hart, and told him about this. And he said, it's the Harvard of Europe. You must go, don't accept anything else. So I went there, stayed there for 2.5 years and did my postdoc with him. It was wonderful, and that's where I got a very good understanding of how to approach systematically using an organic chemist perspective of trying to understand what he called the chemical roots of life. And then I came to the Scripps Institution of Oceanography, where I worked with Gustav Arrhenius as a NASA fellow, and then got recruited by Albert Eschenmoser back again to Scripps Research, where he was asked to start a lab. So I worked with him to start a lab under his, auspices. And then in 2009 he retired, and then I became the PI of the lab, if you will, once he retired. And then I've continued this work, and it has been absolutely fascinating journey for me personally. I've just been having fun doing this.
Since you already mentioned NASA and you guys have been getting funding and somehow you are associated with NASA, right? Can you please talk about it?
Yeah, so initially we were, the work that we were doing here, we were initially at Scripps Research, we were funded exclusively by the Skaggs Institute of Biology, chemical biology. And then slowly, as I began to become part of, excuse me, the NASA, let me just take one. So I got into contact with NASA people by sitting on the panels for review and things like that. And then we started applying for funding by the NASA Astrobiology program, exobiology program. So that's how we slowly got associated with NASA. And slowly the success with our chemistries, the success with our proposals made us even much closer with NASA. And so right now, I'm part of a research coordination network that has been started by Astrobiology, NASA. And that is what I'm part of is called the prebiotic chemistry and the early earth environment called PCE3. And what it aims to do is to bring researchers who worry about the early earth conditions, primarily the Hadean earth, and the type of chemistry that could have gone on considering the early earth constraints, atmosphere, the chemicals that have been available, stable, available for further reactions, and the people who worry about how those kind of prebiotic reactions with those prebiotically available chemicals can transition to what we call life's processes. So that's how I came to be associated with NASA in a short summary.
Yeah, that's fascinating, and of course that interesting work which we'll definitely discuss about. But before that, let's dive into these major worlds or basically major theories in origins of life that they claim or they propose that these or one of those worlds they give rise to modern world.
Yeah.
So can you please give this brief introduction about this different worlds which are proposed?
Yeah, and it is a very logical approach. For example, if you want to understand the origins of life, you look at what life uses, and life uses certain biomolecules like proteins, DNA, RNA, phospholipids, sugars as oligosaccharides. And so what you do is you look at what the fundamental unit of those polymers are, life polymers or life processes are. And you look at, amino acids as the fundamental building block for proteins, the nucleotides as the fundamental building block for RNA and DNA, the simple sugars. And then if you look at the metabolism, the simple keto acids and the carboxylic acids that are used in, say, the reductive TCA cycle, for example. So people then focused on these small units and said, if I can build these small units from the elementary materials that would have been available on early Earth, which would have been like carbon dioxide, for example. If I can convert carbon dioxide to, say, a carboxylic acid, then that would have been the way that things would have started out. Because then if I make the building blocks of life, then somehow they got together to make life. So that led people to look at, the one of the primary influences at that time were, Darwin, and then the Darwin warm little pond. And then a lot of people started thinking about how can soup of chemicals come together. And the breakthrough really came when, at UCSD, Miller, but before that, he was at University of Chicago, did the very famous Urey-Miller spark discharge experiments, which converted gases to building blocks of, say, for example, amino acids. And that gave rise to, many theories saying that, the amino acids which are found in many prebiotic experiments and as well as meteorites, for example. So they, constitute the proteins. Therefore, they could give rise to proteins which are very good catalysts, which can make reactions happen. And therefore, many people thought about this protein world. They said maybe proteins are very simple to form. They came first and they started catalyzing reactions. And then people also started worrying about how you'll get, RNA and DNA. And with the proposal that RNA can act both as a catalyst as well as a replicator, which the proteins cannot do. The proteins cannot replicate by themselves per se. So people started thinking about RNA as the central molecule that would have played a role in getting things started. They can synthesize the proteins, they can replicate and carry information. So that's a molecule that could have started everything. And so the RNA world came about, where RNA was the central molecule that would play the important role. There were people who then objected to that as well, saying that, but RNA is too complicated to self-assemble. It must have come from small molecules. And if you look at biology, how they are made through metabolic processes. So they started thinking about metabolism or metabolic cycles that could have self-assembled to give rise to these building blocks. So metabolism first was a camp that naturally arose as a way to explain chemical origins of life. And but all these cannot happen in isolation. So people said, if you try to do this in an ocean or a pond, it'll all get diluted. So you need to have a kind of an enclosure under which, in which these could happen. And therefore the lipid world was born. The lipids are the ones that would enclose this. So these are, they appear as different camps because they studied these parts separately. And that was the state of affairs for quite some time before people began to realize that these cannot happen in isolation. These things have to happen together. So right now, I would say there is something that is called systems chemistry, where people are trying to put these things together, not study them in isolation. Studying them in isolation is okay for you to understand a proof of principle concept or however things would work. But then when you try to put them together, there is a dynamism that happens that takes it beyond, a simple, peptide formation or just the oligonucleotide formation. The question is, how do they begin to help each other, or do they hinder each other's formation? And how do the chemicals evolve or the reactions evolve when things are put together? So right now, the situation is that still there is a fair number of people who believe, that RNA world is the way to go, or metabolism is the way to go, and they have opposing views as to whether they coexisted or not. But I, have kind of, taken away myself from all belonging to any of these camps. And what we try to do in our lab is to take an approach which is non-teleological. That is to say, we do not know where these chemistry will lead us, and we are trying to let the chemistry under a certain defined conditions tell us what happens, rather than actually look for what happens in biology already in our experiments.
Yeah. And so, I mean, one reason why RNA world is a favorite of most of the scientists is that because RNA serves the purpose of that storage molecule, which stores the information, but it also can, catalyze the reactions. Means
Yes.
so basically, it can store the information for the genetics. It can, of course, catalyze the reactions for the energetics. Of course, if there is any link with the RNA and lipids, that will basically cover those,
Correct.
the
Yep.
crucial parts of the whole machinery, right?
Yep.
So what's your view against it? I mean, do you think that if they find these links, it's still not or can't do the job?
No, you are talking at a level, of a polymer, a functional polymer. I am far away from a functional polymer. I'm trying to put the building blocks of those polymers together. Now, the problem comes as the following. So, for example, if you take a look at RNA, and let us take the pyrimidines, the cytidine and uridine, for example. Those, so you have cytosine as the nucleobase and the uracil as the nucleobase. And those are formed by simple reactions from HCN. So, for example, if you take HCN, it makes a polymer and you hydrolyze it, you get uracil and you get cytosine from that. So people say, look, the simple chemistry gives us cytosine and uracil. RNA uses cytosine and uracil. Therefore, it's very simple. So once I make cytosine and uracil, there is a functional RNA. But that is far from the truth. You can't just take only the uracil and cytosine and make RNA. And that is a well-known problem, what is called the nucleosidation issue. So forming the full nucleobases or the full sugar does not get you to RNA. Rather, if you look at biology as to how these uridine and cytidine are made, they are made from a molecule called orotidine, which you might recognize. It has the carboxylate at the C6 position. Now, what nature does is it takes orotic acid, which is synthesized from aspartate, and then attaches it to the ribo 5' pyrophosphate via enzyme catalyzed reaction, and then makes the orotidine, which then it decarboxylates to give uridine. The uridine is aminated to give cytidine. Nature till today does not synthesize uracil or cytosine biologically. The only nucleobase it makes fully is orotic acid. Okay. Now, if you go and look at the hydrogen cyanide reaction that I said, which gives uracil and cytosine as nucleobases apart from adenine, it also produces orotic acid. But people are not excited about orotic acid in prebiotic chemistry simply by the fact that biology does not use it in the final RNA. And that is a mistake, in my opinion, because what you're doing is you're taking the finished product, which is an evolved, selected product through many selection criteria, and then taking it to a level of just the nucleobase where there is no criteria for selection based on the function of RNA. So all the functions that you mentioned of RNA, information, replication, interaction with phospholipids, etc., are not at the level of a nucleobase of cytosine or uracil. So once I make uracil and cytosine, how do I select for RNA when that function has not appeared? How do I select when there is no function of all the beautiful things that RNA does? I can't select for it. So my problem with that RNA world is not that they are able to demonstrate wonderful things of what RNA can do, but trying to take that and extrapolate it to a level where there is no selection criteria of an RNA. And that is the disconnect. People forget, they talk about RNA can self-replicate, RNA can, do this, etc., etc. But the problem is none of that happens at the level of a mononucleotide. Mononucleotides don't base pair. Mononucleotides don't self-replicate. Mononucleotides do nothing that RNA can do. So you're talking about a highly sophisticated oligomer or a polymer properties versus a property that doesn't exist at the level of a monomer. That's the disconnect that I have with the RNA world.
This is very interesting. Let's talk a bit more about it. So what I remember from the evolutionary biology point of view, right? So when, of course, now, of course, many people, they are talking about evolutionary theory. And so the way they deal with this issue is that they say that once we reach to the genetics, with certain processes, of course, those certain processes are that you are dealing with. But once we are dealing with these certain processes and we reach to genetics, then simply evolution and natural selection, they can take over to give the diverse forms of life that we see on Earth, right? We can push that point a bit more, and we can say that with certain processes, once we get a kind of RNA molecule which can do the job, then it can go and give us the primitive or protocells, which can further take the process. So at least we are pushing that point a little bit further. But then, of course, you are working beyond RNA. That's how those the conditions in this prebiotic environment gives rise to this RNA molecule a kind of thing, and then how the life after that forms, and how then that life can take the process of evolution, right?
Yeah. So let us even take that, one sentence where you say, once we have a self-replicating RNA can make the components of a protocell. Now, to show that experimentally would be nice, but nobody has shown it, and I'm not saying it cannot be done. It can be done, or it should be done, or people should try it. But unless that is made, that is experimentally shown, that sentence that once an RNA molecule, self-replicating RNA molecule is formed and everything flows from that, for me is like they lived happily ever after fairy tale ending. What you're saying is once I get to RNA, everything will flow. That is only a hypothesis. It might be a good one, but it needs to be experimentally demonstrated. Unless that is shown, that still belongs to the same level of hypothetical credibility, as people would say, whoa, once a metabolic cycle is formed, everything else would follow. So if you do not accept that once a metabolic cycle would form and everything would follow, why should we accept the other statement that once a self-replicating RNA would form, everything would follow? Right? You see the point. The same weaknesses or strengths apply to both of them. And my point is the following: if you make a self-replicating RNA, that self-replicating RNA needs to also make its own building blocks, which has not been done. So once you get to an RNA that is able to make let's say, the cell components, how does it make itself? What processes does it do? And what processes does it develop? Now, people have been, it's not for lack of trying, people have tried, and people are trying to say, there was this very famous paper by, I think, Barton, who showed that there is a ribozyme that can put on a nucleobase on a sugar. No, those are the kind of experiments that will give them the confidence that RNA enzymes, once developed, can begin to show these kind of functions. And I had an interesting conversation with one of the top RNA world experts some years ago, when they were showing different functions of ribozymes. A ribozyme can do this, a ribozyme can do that. And my question to them was, are you trying to teach an old dog new tricks? Right? So it could be that, yes, we can demonstrate. And, I think those are two separate questions. One is trying to go back in history and say it happened this way. And the other is it can happen this way. And I'm supporter of it can happen this way, because that shows a self-replicating RNA molecule can do these things. Whether it did it or not, that's a different story. But the moment you can show it can happen, that itself is a good experimental way to move towards processes that begin to exhibit properties, lifelike properties.
Exactly. Yeah. But then, I mean, it can be RNA or it can be any other molecule that we can find, and we can say that if it is self-sustaining enough, we should be happy to accept it, right? That this is the actual, this is what we are looking for. But the other, so I mean, of course, before you explain the whole chemistry, how to get RNA, but maybe we can simplify a bit and talk about if anyone has done this Urey Miller kind of experiment where they kind of try to mimic this prebiotic environment and try to get these kind of building blocks. So what do they get there in terms of building blocks for nucleic acids, like for RNA or something?
So in the classical Urey Miller experiment, people have gone only after amino acids, and you can, with certain variations in the conditions, which later people have shown, you can try to look for nucleobases that would be formed. But the problem is, when you want to go look for something, you're looking for something that is already known in biology, right? You have to look for standards, or how will you detect? How can you search for an unknown molecule, right? So, but the thing is, there are a lot more other molecules than just the molecules that you want in biology as well. So that means they are one among hundreds of thousands. So you will find uracil. For example, Stanley Miller did another fantastic experiment, which is not as famous as the gas discharge. What he did was he took ammonia and hydrogen cyanide. So it's basically ammonium cyanide. And they made a solution of it, and they put it at minus 78 degrees in a freezer. And they forgot about it for 28 years. So once Stanley was retiring and UCSD, they were clearing out his lab, they found this vial, and it had turned pitch black completely. And so when they took that and they analyzed it by hydrolysis, they found a lot of nucleobases as well. So, you can have, different ways of producing these molecules, not necessarily by the spark discharge from the gases, but can also happen from simple molecule like an ammonium cyanide solution, where you can get plenty. But the problem is, it's not it's, we are intrigued by the connection between something that we know. It's like we are going into a foreign country and we are looking for familiar places. And the moment we see a familiar face, we gravitate towards that, right? So it's something similar to that. In these mixture of molecules that are being produced, in the thousands, we look for molecules that give us immediate validation. Oh, these kind of, what it tells us is that that kind of structure and that kind of chemistry is elementary. What it means for a life to emerge, that's a completely different story. As you very well know, you can't just put all the mixtures of chemicals or all the mixtures of RNA and phospholipids and proteins and have a living cell, right? There is some, I'm not implying anything mystical, but what I'm trying to say is the emergence of a life process that is self-sustaining is much more than a mix of chemicals. So just because I made a chemical or just because I made a reaction, it would be not very productive to immediately, go forward and say, life. That's what I'm trying to say.
So on one hand, you are saying that we should not be guided by the present biochemistry that we have.
I'll give you a very good example for that, and we showed this in a paper. For example, let us take amino acids, right? So Urey-Miller experiment produces amino acids and plenty of amino acids in the meteorites. So people said, let's take amino acids and convert them to peptides, and peptides will make proteins, right? And people have tried. But the problem with starting with only protein, only amino acids, is twofold. One, it's not prebiotically possible because there is no prebiotic scenario where you produce only amino acids. So how do you separate them from the mixture? The second is that if you start only with amino acids, because amino acids are zwitterionic, it's very difficult to polymerize them. You need extreme heat, like 130 degrees or above, or you need to use activating agents to make that go. And then you have to argue whether that activating agent would be available on early Earth, along with the amino acids, and those kind of things. Actually, when you look at the prebiotic chemical inventory of where these amino acids are produced, you find alpha hydroxy acids as well. The meteorites contain a lot of alpha hydroxy acids. Miller-Urey experiment produces a lot of alpha hydroxy acids. So what we did was we took alpha hydroxy acids and amino acids and put them together and just dried them down and wetted them and dried them. And we repeated the process, heating to about 80 degrees centigrade. And what we found by mass spec was that if you start only with amino acids, you don't get any peptide formation. If you start with alpha hydroxy acids alone, you get a lot of polyesters formation. And if you mix the amino acids and alpha hydroxy acids together, what you get is deoxypeptides. These are oligomers which have ester bonds and amino peptide bonds mixed together. And if you keep repeating it enough, what happens is the peptide bonds are enriched in the final oligomer that you analyze by mass spec. And the reason is kinetically, it is easier to form an ester bond. And the amide bond that is formed by the attack of that NH2 of the amino acid on the ester bond leads to a thermodynamically stable peptide bond. So it's the interplay of kinetics versus thermodynamics that allows you to accumulate peptide bonds naturally as a natural outcome. And the nice thing is, if you look at how the ribosome makes the peptides, it's exactly the same mechanism. The tRNA is charged with an amino acid through an ester bond. And it brings two of these amino acids next to each other, right? The acylated tRNA. And then the NH2 group attacks the other ester bond, and it's the same principle. So for us, getting to a peptide bond is much easier if you start with a mixture rather than you start with pure amino acids. So if you went only by biology, which was using only amino acids and does not use alpha hydroxy acids, you are still stuck with trying to get only peptides from amino acids. Rather, if you use the mixtures that are naturally given in a prebiotic environment of alpha hydroxy acid and alpha amino acids, the peptide bond is a natural chemical and behavior. So for us, that is more intellectually satisfying rather than looking only at biology and saying, I want only amino acids in prebiotic chemistry. So there is an example where you can use prebiotic chemistry and connect it to biology in a natural chemical fashion.
Yeah, but since you before already said that the life is not about mixing chemicals, right? But then, of course, at the end, you are mixing chemicals. So
Yes, but
what's the
for us,
difference?
yeah,
Mhm.
you raise a very good point. But what we are claiming is not life there. What we are trying to say is the chemistry that naturally emerges from a mixture is also reflected in biology, which is the simple ester amide exchange. That's what the ribosome does so nicely. So that means in order to take that mixture, that chemical reaction that we showed in a mixture, and to move it to a level that would sustain life, you need catalysts. We didn't use any catalysts there. We just used heat. And the question is, simple heating is not going to get you to a life process which is self-sustaining. And so that's why I'm saying we use the chemical mixtures to demonstrate that the type of chemistries that you see in biology are a natural outcome and not something that biology has invented, per se later. Because one of the things that my, mentor Eshin Moser used to tell, and which is very true, is enzymes do not create new reactions. They only optimize existing ones. That means that reaction has to exist for an enzyme to operate on.
Yeah. Cool. So the one thing that or is there any evidence, or what is the consensus among scientists about multiple origins of life? That there was diverse chemistry already, and then I mean, of course, one lineage survived, which is us, basically based on nucleic acids and proteins, etc., lipids. But then there could be other sort of wide variety of chemistry which may have existed, and we may have had certain unicellular organisms based on that. But of course, it'll be really difficult to spot it now, right?
Yeah, correct. You are absolutely right. So those are legitimate ways of thinking about, different ways of origins of life. And, you come to a certain point where one process really took over because it survived better than the others. It out-survived the others, if you will. So people talk about LUCA as one of those kind of things as well. They say that LUCA is not there was not only one LUCA, there were many LUCAs, that only one survived to go forward. So your question is at the same vein, but with respect to the much deeper chemistry that could have given rise to that. And that is a very legitimate approach. There are people who take that approach, and you can say the 5 different approaches that we talked about: metabolism first, RNA first, or protein first, would fall into those kind of categories, right? So people are trying to say, no, this molecule came first and gave rise to that, those kind of things. But there are people, people who work with hydrothermal vent scenario. There are people who work with a pond scenario. There are people who work with, more like a wet dry scenario at the interface of a lake and its shore kind of things. There are people who work with shallow hydrothermal vents, not the deep hydrothermal vents. So there are a lot of people looking at different things, and we should let the chemistry and the experimental evidence play out rather than shutting them out per se.
Because for me, interesting thing is the oxygen, right, which basically came a
Much
bit
later.
later in
Yeah.
the environment, in Earth's environment. So it'll be very interesting to know whether some unicellular organisms existed without like with the whole chemistry without the oxygen, etc. Or it's like, what's your understanding there?
So the understanding that I get from my colleagues when I talk to them is that, it was largely an anoxic atmosphere about 4 billion years ago. And if life originated, it must have used anoxic resources such as carbon dioxide. There are methanogens and, other things that, could have, gotten life processes started. one of the things that I always struggle with in looking at very ancient life and then trying to make claims about the chemistry that existed before is the following. Is that whether are we confusing origination, with adaptation? So, for example, when people point out to the deep hydrothermal vents, they point out to look, how life is using the reduced energy that is coming out of there, the hydrogen, things like that. And they say, since life adapted to that extreme conditions, or life exists under those extreme conditions, it must have originated under those extreme conditions. But the problem is the following. Life can exist under those extreme conditions, but the individual molecules per se do not. For example, you can't put an oligomer of RNA under those conditions and expect it to survive for a reasonable amount of time for it to do all the things that an RNA world would want to be done. RNA would simply hydrolyze under those conditions. Many molecules are not that stable under those extreme conditions per se. And people have argued against that. It's not simply my opinion here. The problem is the following in terms of trying to take simple chemistries that would lead to the building blocks that would lead to the life form that is there. Those are very different stages that one needs to be cognizant of. Just because you see the finished product surviving at that condition doesn't mean that that finished product was made at that point. It was probably something that came and adapted itself with it. And I'll give you a very practical example. If you go to Japan, you see these beautiful tall rise buildings that survive earthquakes. They survive, really big earthquakes, and, they sway, they don't break apart. People live there all the time. But the question then becomes, that building was built to survive the earthquake, but you can't make the argument that it was made during the earthquake. During the earthquake, they don't build, they built it after the earthquake when it was stable in order for it to survive another earthquake. So the same way, the building blocks of life are not stable under those hydrothermal vent conditions. People forget that. They can do wonderful reactions, don't get me wrong. They can try to reduce carbon dioxide to formate or acetate. They can produce those kind of small molecules, but they can't take it further. They can't, do an RNA replication under those hydrothermal vent conditions. I've seen people claim, oh, I can make oligomers under this hydrothermal vent conditions. But if you look at that chemistry very closely, they already use activated molecules like phosphorimidazolides, but they don't tell how those phosphorimidazolides can be formed under those hydrothermal conditions. So there are inbuilt biases for people. One has to be very, very careful before making this grand claim that, origin of life at hydrothermal vents. The same is true for, the RNA world. The same is true for the metabolism world first. So that is why I'm very skeptical of all these, this world gave rise to origin of life. Okay. So.
Yeah, I think at this point, probably we can also talk about this news that I was reading about your work. It was Indian origin chemist finds new clue to how life began on Earth. So,
yeah, that is the news agency trying to get hits and likes versus us who just say, look, we just showed a chemical process that may be of interest to origins of life. So, it gets filtered through and, it's like we just draw a circle, but then that circle gets, an eyebrow and a face and a paint, and then suddenly becomes a live entity by the time it gets to the press. And I don't fault them, because that's the way science is being made, I would say, available to the lay people, because everything is now in a democratized way where the lay people's public tax dollars funds the science. So you have to get it back to them somehow, that they begin to appreciate or show interest in what this type of chemistry and science is being done. So unfortunately, many times the science gets blown up too much. One example would be not just our work, but also the case of phosphine and life on Venus. The the paper that they published was very cautious, but not cautious enough, in my opinion. But they left it open for this kind of hype that would follow. That the trace of phosphine, which is itself is questionable, that was discovered on Venus, was a biotic source and therefore life. So one has to be guarded among these kind of statements that you see when you say they find new clues to origins of life. I've seen this. We have been part of this. I've seen my colleagues go through this, and we all smile and with a knowing smile we just say yes and we just move on. But try to do really good science and not be distracted by these kind of headlines.
Yeah. I think you are raising a very good point. I mean, of course, we need to kind of popularize the science, but we also need to, I mean, of course, we admit the truth that we don't know yet how the origin of life.
Yeah, but when you say we do not know yet, that doesn't make a good headline for a news agency.
Yes. Yeah. But again, since, I mean, I think many people that they are interested in science and they at least they are understanding science, the process of science bit better, that it is an evolving process.
Yeah.
And that's the thing that, so if we talk, if we start talking about this Urey Miller experiment, which happened last century, to till now, at least there have been some developments, right? That there are certain processes that we understand a bit more. So just to highlight the, that positive line as well, that we are moving in certain directions. I mean, for example, this work that is coming from your lab, that at least from certain mixture, we can get a chemical process that is already kind of that positive.
And that work that I think you're referring to the cyanide work that appeared. That work really showed that there is a different way of thinking. Because when you think about the citric acid cycle and the transformation that takes place, there is a very nice paper by Leslie Orgo in PLOS 1, where he argued that the reductive citric acid cycle, as which is known in biology, cannot operate in a completely enzyme-free conditions, in an abiotic condition. It will be very difficult to do selective transformations because the molecules look very similar to each other. There are many keto acids which will undergo the same chemistry if you try to do it only on one. So one example will be oxaloacetate going to malate. That reduction will also reduce pyruvate or alpha ketoglutarate or any other keto acid that could be there. But what we found was the cyanide is able to actually mediate only that reduction of oxaloacetate to malate without reducing pyruvate or alpha ketoglutarate. And that is an example of thinking how a sophisticated function of selective reduction of a carbonyl group can happen abiotically by a simple molecule like cyanide, which could have been present on early Earth. So that frees you from thinking, oh, I have to do or replicate what the enzymes do, because the enzymes use metal cofactors, metals and cofactors. And the question is, so people think, let me strip out the whole enzyme and then use only the metals to do the reaction. But the problem is, if you use just metals, they do a lot more harm than good for the reaction, because they do radical type reactions, they destroy molecules, then making more of them. But here the cyanide does not destroy them. So it's a different way. I'm not claiming that this is the way it should have happened on earlier by any stretch. But what I'm saying is it can happen in the absence of enzymes by a simple molecule. So that opens up the possibility for you to think differently and in a simplified way, and not be tied to how biology operates and extrapolated to prebiotic chemistry.
Yeah. So if now let's say that, I mean, the way you explain that really makes sense, that if we if we don't go with the modern biochemistry, right? That if mainly the pre-biochemists, if they're focusing more on the more primitive chemistry, and then trying to see where they reach with these large polymers, right? The point is that how do you look at it in the exobiology setup? So let's say if so since we are designing certain missions on
Yeah.
other planets, right? And if we find certain building blocks there, so then how do we link these two observations?
It's a very good question, one that we wrestle with all the time, because one of NASA's primary mission, or the primary mission, is to take this chemistry that we all study here and ask the question, is there life out there? And what are the criteria we will use to go and detect life or signs of past life? So one of the things that people have focused on is chirality. Chirality is very special to life. And the question is, if we detect chiral molecules, can we take that as a sign of life or not? There are pros and cons to those kind of arguments. The other possibility is to look for small molecules that would come only as as a result of life. But again, we are limiting to the type of life that we know that exists on Earth, and we may be misled if there was another type of life which is based on a completely different type of chemistries. Even in our own Earth, if you look at life based on RNA, DNA, proteins, phospholipids, sugars, it has been so because it was influenced by the environment under which the chemistry took place. For example, you find life at very extreme conditions like pH 2, 3 or pH 11, 10, 11. And your organic molecules like RNA would not function at that pH. You take RNA and put it at a pH 2 water, it will go away. pH 10 water, it will go away. But how do these organisms survive? They do it by controlling the pH within them by either pumping the protons out or keeping the protons in, depending on the acidic or basic environment they are in. So that means they need functionalized proteins, or they increase their GC content if they are living at very high temperatures in order to stabilize the double helix so that it doesn't separate. So you see, immediately they are adaptations to the extreme conditions. But so that means life evolved around a zone of pH 6 to 8, roughly. So if your early oceans and early waters and early Earth was always at a pH 2, then the molecule like RNA would have never developed. You would have had a completely different molecule which could have functioned at pH 2. So now take this to the exoplanet level, right? If you have an atmosphere that is completely different, but with organic molecules, what sort of life would come about there? So we can actually explore those kind of things in an environmental setting here by making different backbones, by making different nucleobases that would be able to base pair at pH 2, for example, and have an informational system that functions only between the ranges of pH 2 and 4, for example, or pH 9 and 10. Then you are talking about alternative life, right? So there are different ways to go about doing it, but right now the most practical thing is, does life as we know it on early Earth exist outside, and use those kind of markers to answer that question. One question was oxygen. Oxygen came 2.5 billion years ago, right? So many people argue, like, if you do that, then you may miss that first 2.5 billion years where there was really no signature for oxygen. So you see, you are caught in a bind when you use one marker, because that's using that same marker might defeat the purpose of finding life for you. So that is where we are. Even though it comes across there are so many factors, but there are people making very good progress and trying to be very strict, given the past mishaps that we have had with claims of life on Mars or claims of life on Martian meteorites and things like that. So it has to be taken very slowly, very carefully.
And what do you think about this Goldilocks zone hypothesis? Means, the way it is defined that since we have the life on this planet and we know the conditions here, we know the chemistry, this is what we should find elsewhere.
So
So,
that is a very reasonable approach, right? It's a very reasonable approach because it makes your task much easier. The question is, are we, by using this approach, do we miss certain points? Like it's like, we are so focused on using this criteria that if there are beginnings of life elsewhere which have not yet come to this level, do we miss those kind of things? Or if it is something completely based on a total different chemistry, how do we know we would get that? So those are very, very difficult questions for which I, at my level of understanding, do not have a clear answer.
yeah. The other aspect when it comes to these kind of difficult questions is the role of something mystical, like some creator or something,
Yeah.
right? And as a scientist working on an origin of life, I mean, first of all, probably you can talk about your inclination. What do you think about faith?
Yeah.
What's your faith? And then how do you look at this problem when it comes to this philosophy of religion, etc.?
It's a very good question. And I do not know whether you have seen Carl Sagan's Cosmos.
No, no,
No,
that
it's something that you should see. And in that, Carl Sagan, who is an atheist, nobody would call him in any way, shape, or form who believes in a creator. There is, I think it is episode, I think it's episode 11, I think 10 or 11, I forget. And it's something that where he really goes into the section, and he actually asks this question about the creator God and goes through certain things. And the funny thing is, when he wants to say that there is no creator who would be involved in this kind of creation, which place he ends up in to show that?
which
He ends
place?
up he ends up in Tamil Nadu.
Oh, great.
And he picks up the Vedas, he picks up the Upanishads to show that there is no creator per se. That is the last place you would even think that an atheist would go to, get support for his. He talks about the Big Bang theory and he talks about the age of the universe. And he comes to the conclusion, and it's in his video, it's not mine, it's there in his video, where he takes the age calculated by the Vedas and by the Upanishads and by the modern cosmology, and they are within a margin of error of very little. One is about 14 billion years, the other is 13.9 billion years. So now imagine how the ancients, I'm not saying that it is unique to the Indian area, but it must have been throughout, but it must have been masked by other thought process that evolved, that it was lost but somehow retained in India in its very pristine form. But the Indian philosophy or the Eastern philosophy allows different levels of acceptance. And one of the level of, when you go to very far, is there is no need for a creator actually. They don't talk about a creator, but they talk about manifestation. That means things manifest. And they don't talk about at a different level they talk about a creator God. But if you go to the higher level, if you take up the some of the sayings in the Kenopanishad, they talk about gods even coming after creation, if you will. So that's how deep the thought process has been in our Indian philosophy. I can't talk about the other philosophies much because I have not widely read that, but I'm sure that there must be these kind of principles there, but they have gotten overshadowed by a creator God more because that has been more popular or more appealing to many of the followers. So in that episode, Carl Sagan quotes the Upanishads And he really goes into a very lengthy, discussion about how the Eastern philosophy, particularly the Indian Vedantic and Indian Upanishad philosophy, comes the closest in explaining the so-called, the manifestations that we see today. And for me, as a person who, obviously, religious from all these markings and things like that, if you believe in, or if you are convinced in this manifestation approach rather than a creation approach, there is no dichotomy between what I do and what I practice. Because if you go by what is known as an Advaita philosophy, a non-dual philosophy, when there is no second, there is the only one. When there is no second, there is no creation per se. And I've talked about this in quite extent in my writings in some of the journals which ask for such things, and also to lay audiences who have requested these kind of things. And the simplest thing is this, we confuse two concepts. One is called reason, the other is called purpose. So when you want to invoke a creator, you invoke a purposeful creator. But when you talk about reasons and you look for reasons, you don't need a creator. Things happen for a reason, right? But they don't need to have a purpose. So one example I give is fire. So you take fire, and with this fire, you can cook a good meal, right? You can shed warmth to people during cold weather. With the fire, you can burn a book, right? So the question is, what is the purpose of fire? For each action of the fire, there was a reason. The fire gives off light and heat, and therefore it does all the three things that we mentioned. But the purpose of the fire was not to read the book. The purpose of the fire was not to burn the book. The purpose of the fire was not to cook. That purpose was invented by a person who knew how to use the fire. So to impose that purpose on a fire which has no purpose, that is where you run into this issue of why was fire created? And then you invoke a purpose, and therefore a purposeful creator for the fire. But that is absolutely not necessary. So if you keep the reason and purpose separate, and the purpose comes once a sentient being knows how to use it, and the reason is there all the time, then you have no qualms about, a creator versus manifestation.
Yeah, the only thing is, I think then the reason part would be more subjective. I mean, probably, like if someone wants to think that, that he or she wants, or, this is like their reason to believe in something, right?
Oh, sure.
Rather
And
than,
they should be free to do that, because one of the things that you would have seen, in the Indian philosophical system is that there is no imposition of, these ideas. Everybody is free to believe in whatever level they are comfortable, and you will automatically, once that falls away, you will move to whatever level is next comfortable for you. That's a natural progression that happens. It's a very natural progression as it is in. So when I talk about reason, the reason I'm talking about are factual reasons, not the reasons given by a sentient being, because that involves a purpose. Why are we going? Why did I come to the US? The reason is that I could study here or do research, but that is something that I wanted to do. So I can't confuse that wanting to do with the reason. That's a reasoning by a sentient being. What I'm talking about is the reason for the fire to burn something, or the reason for the fire to illuminate something. Those are something innate to the fire by the property of the heat and the light that it gives, whether it likes it or not.
yeah, can you please a little bit expand this reason part? Like, in which sense do you think that it can exist?
Reason in the sense, so that means I'm talking about the reason. So for example, let us say why is cyanide poisonous? What is the reason cyanide is poisonous? Then you begin to say, oh, cyanide interacts with these molecules, it interferes with these metabolic processes. So that is a reason for why cyanide is poisonous. Those are the things when I mean by reason. Now, why did that person die by cyanide poisoning? Or, why did this person die by this method? People might say, oh, those are, you can give a lot of reasons for their death, either from a factual reasoning that they were involved in an accident versus the question of why did that accident happen? Now, that's a different story. So when you ask the question why the accident happened, that can give you levels of reasons, right? One might say he was a sinner. The other might say he was at the wrong place at the wrong time. And the other would say, no, because the two cars hit and this person was there, he died. So those are three different reasons that you can give. And you pick and choose the reason that is best comfortable to your heart. I'll give you another example. This was actually given to me by my colleague at Georgia Tech when we had the Center for Chemical Evolution. And, we got into discussing this because we had to reach out. We had public outreach to, the lay public of the chemical evolution versus the type of, teachings that are there. And he said, there used to be lightning strikes, which would strike, in ancient times, huts, and they would burst into flames and people would die. And therefore, people said, oh, that person maybe lived a sinner's life and, the lightning struck them and therefore they died. But then people came up with the lightning arrestor. They put up a big lightning arrestor, which took all the lightning and people did not die from lightning strikes. Now tell me, that did putting up the lightning arrestor do away with the sins of the people? So we are attributing, reasons that are beyond our comprehension to explain things that are not easily explainable. But it need not be the case. That's my submission.
So the question was I because I'm not able to understand when you talk about God, right?
Yeah.
We are talking about, so at least from your explanation, we are talking about a purposeless God for certain reason, right? So
when we, the term God, I need to understand because I'm a scientist, and I can't use a term when I do not understand that very well. So when people ask me, do you believe in a God? Many people have asked me that. My question to them is, can you define that God that you're talking about? So if they can't define that God, then I cannot answer them. But if they define a God with, it must be a God that is defined by this religion or as a God defined by that religion, then it becomes an issue, because how can a universal truth be so different? Right? A universal truth is a universal truth, irrespective of whatever the situation is. So when you begin to talk about different religions believing in different types of gods, then what it tells me is that they are seeing the same universal aspect, but in a limited form. And I can explain this to you very easily, which I do to many of my audiences. So I get high school children who come and, where I give them talk about religion and philosophy. And one of the exercises that I do for all of them is I pick about 3 or 4 people and ask them to write down the directions from their home to their school. They come from a same school. So, they all write down their direction. They have GPS, they show me all that. Then I ask them to exchange the phones. And then I say, follow this direction from your house. And they will not end up in the school, because the directions was different for each of them, even though the destination is the same. Right? So you can't take one person's direction that was given to them because they were born in a particular religion and take it and give it to another person because you think it's the best pathway. It's the best pathway for you because your destination and your relationship is very different from that person and that destination, which may be the same, but the pathways are different. So after that, they enjoyed it. They enjoy it, saying that, oh, I can understand. Just as you can accept somebody lives in a different house and comes to the same office using a different route, except the same way that people have different faiths, but they come to the same place using their routes. And then you will not run into this issue of, whose God is correct or which God is correct or whatever.
Yeah. No, in my case, I'm an atheist.
Yeah.
So I don't, because I'm just trying to understand that if, especially a scientist who is working on origins of life, where does that scientist, so first of all, like, what do you think of a creator? And then where do you, or as you said, that for you, a creator is what, a purposeless, I don't know.
No, the question is, Richard Dawkins, right?
Yeah.
He wrote a very famous book, and it was titled The Blind Watchmaker.
Mm-hmm.
And people argued about the title, and they still do, because he said the watchmaker is blind, right? That means he doesn't know what he's doing, but there is still a watchmaker. So who is that watchmaker? Or what is that watchmaker, right? You can call it nature. It might be simply nature. What we call as nature and a natural process for others might be a God and a creator. And, when I have this kind of talk with many people, I say, calling it by different names and calling it, one which has a purpose and one which has no purpose, it's their way of expressing their understanding. And taking that example that I gave you before, that is their pathway from where they are to that same destination. And so let that be, we don't need to convince them. And there is no, in my opinion, there is no need to convince them about that. Let them be, let them have their beliefs, and we have our beliefs, if you will. Like people believe in an RNA world, people believe in a metabolism only world, right? So those are also beliefs. They are different pathways to reach to the same destination of understanding the origins of life.
Yeah, but scientists, they falsify. So it's just that you need to kind of understand.
So that goes to the personality, and it goes to that person who falsifies in science probably is also falsifying in other areas of their life as well, right? So it's not just the science part. So it goes to a personality defect part.
Yes. Yeah, this is amazing. I mean, it's amazing discussion. And I always try to understand that when we are working with all these, I mean, these are difficult questions. These are like basis of our life, right? And then of course, if you're working, then you also think of different philosophy which has been around for all these years, right?
Yeah. In our philosophy, you talked about a creator, existence of creator. One of the highest statements that are made at that level, not claiming that, certainly not at that level, is aham brahmasmi. When you say that, there is no creator. But it's very difficult to live that aham brahmasmi in a practical way. And therefore, that is an ideal state. You may remember in chemistry, we study about these ideal states which are never attainable, at least by the molecules. It's that kind of an ideal state.
Yeah. Yeah. This is really interesting. So what are the other questions that you are interested in, or your lab is focusing on
So
nowadays?
exactly, the type of chemistries that we have published now, we are trying to see how naturally they can emerge under what conditions to give rise to the next set of molecules. So for example, the paper that we published shows a simpler version of a citric acid cycle, what we call the reductive glyoxylate pathway. So the question is how that chemistry can produce the next set of building blocks. For example, if we involve, here we had only cyanide and keto acids. What happens if we throw in ammonia? What happens if we throw in carbon dioxide? What happens if we throw in other molecules? What naturally comes out without any expectations that it must be this, what biology uses? Let us see where the chemistry takes us. And if the chemistry happens to produce something that what biology is using, then we may begin to get some traction of how the system might move towards what biology is doing. that's where we are.
And what about further reading? I mean, if people they won't read, I don't know, of course, your work, which I will list in the information of the video, but
Yeah.
other scientists that they can follow and read more about these issues.
So there is a very nice book by Addie Pross, that talks about the origins of life, from chemical all the way to biology. Then there is also another book, I think it's called The Eighth Day of Creation. It's a very fascinating book. I forget the author's name, Eighth Day of Creation, which talks about how molecular biology really developed. It is a very fascinating, it's a huge, thick book, but it's a fascinating read about how molecular biology, the field of molecular biology developed. It takes you through the fascinating first-hand accounts with Watson, Crick, all the major players, developing the genetic code and how it was developed and how it goes, and it really puts it in the perspective, and of course people who really want to be very critical in thinking about this, Richard Dawkins, the Blind Watchman, that
Yeah,
would be
great.
the other extreme. Yeah.
Yeah. So thank you so much for accepting the invitation, coming onto the podcast, discussing not only your research, also your philosophy, your understanding of these complex issues. Thank you so much for that.
Yeah, and thanks again for this wonderful opportunity. And I hope that people who see this take it in the right spirit, and nothing was said to offend anybody. So